In the previous video, I talked about case 1 of portfolio theory, and in this video, I will talk about case 2 of portfolio theory. Okay, so just to remind you what case 2 was. The case 2 was where the losses are IID, right? And n is the number of investments, is itself is a random variable, and we need to assume that n is a random variable independent of the losses. This is a crucial assumption because we cannot do the calculations otherwise. So the number of investments is a random variable independent of the losses. All right, so let's consider the first variable, which is the total portfolio loss. The Cdf of S, which is the total portfolio loss, is given by, this is the notation I'm using, and by definition this is the probability that capital S is less than or equal to a fixed number. Now in the next step I'm going to use right. This is a result you should be familiar with. You should not. Let me say what it is. This is because of what is known as total probability rule. You ought to have covered this in probability 1 in your first year courses, right? So it says that this you can write as the sum of this conditional probability that of S given n is the number of investment, times the probability of n. N goes from 1 to infinity because the number of investments cannot be 0, right? So it has to be minimum equal to 1. All right, now in the next step, this conditional probability here of S given that capital N equal to little n, this is the same as what we worked out in case 1. Because in case 1 we assumed that the number of investments is fixed. And that's what we are saying here. When capital N equal to little n, we are saying that we are fixing the number of investments. So because of what we did in case 1, what we got in case 1, we can replace the conditional probability by simply this. Right, and this multiplied by the probability that capital N equal to little n. So this result here, right? The step from this line to this line comes because of what the result that we got in case 1. Okay. All right. So this is the formula for the Cdf of S under case 2. Now the PDF of S PDF of S is simply the derivative of the CDF of S, right? Okay, that's variable A. Now variable B is the minimum portfolio loss. So okay, here we are. This is B. Right, so this is the notation I'm using. It's the probability that capital U is less than or equal to a fixed number. And once again, using the total probability rule, we can write this as the sum from 1 to infinity of the conditional probability that capital U given capital N equal to N times the probability that capital N equal to N. So this is the, once again, I have used the total, the probability rule. Okay. All right, in the next step, I'm going to replace the conditional probability with what we got in case 1. And you probably remember what we got in case 1. So remember, the distribution for U that we got in case 1 was this. So this is the result that we got. This is the result that we got in case 1. Right. Now we can simplify this further. Because you have 1 minus, you can put this as 2 different sums. Right, so you get 2 different sums. Now the first sum is the sum of all the probabilities, therefore it must be 1. Okay, so this is simply 1 minus the sum from 1 to infinity So this is the formula for the CDF of minimum portfolio loss under case 2. The PDF Alright. The PDF, you just simply differentiate the CDF with respect to U. And if you do that, this is what you will get. Alright, so that's variable B. And third is the third variable of interest is the maximum portfolio loss. Alright, so C the Cdf of V is this. Once again, I'm going to use the total probability rule. So you can write this probability as the sum from 1 to infinity of the conditional probability given that the number of investments is fixed times the probability that capital N equal to little n. So once again, I have used the total probability rule. Okay. Now in the next line, I'm gonna replace the conditional probability with the result that we got in case 1, right? Which is this. Okay, so this is using the result in case 1. Right. Okay, now this is the CDF. The PDF of V is just simply the derivative so if you differentiate this with respect to V, this is what you will get. You will get the following. Okay. All right. So those are the 3 variables, right? All right, now I'm going to do a couple of examples. So I'll start with one example. This is carrying on from case 1. This is example 4. Suppose IID with n is the number of investments having a geometric distribution with parameter a, right? And the question is to find the distributions of U and V. Okay, so let's start with U first, right? We should use the formula that I gave you in the previous slides. The CDF of U is as follows. It's 1 minus the sum from 1 to infinity of 1 minus the CDF of x at U power n. and times the probability mass function of a geometric variable. I'm sure you know that from first year, Intro to Stats. This is the PMF of the geometric distribution. All right, and this you can simplify, you can rewrite as follows. All right. And in the next step, I'm going to make a substitution. So I'm going to set m equal to n minus 1. Okay. So under this substitution, the sum will become as follows. So in terms of m will go from 0 to infinity. Okay. All right. In the next line, I'm going to use a well-known result. If you don't know this, I will write it down. Or if you don't remember this, you may want to remember this, that if you have something like, this is known as the geometric series, right? Sum from 0 to infinity of z to the power m is equal to 1 divided by 1 minus z. Right? So using this result, you will get the following. You will get so this is the CDF of the minimum portfolio loss. All right. Next, we also want to find the Cdf of V. So let's see how we can do that. The Cdf of V, the maximum portfolio loss. Using the formula I gave you a few slides ago, you can write it like this. Times the probability mass function of a geometric distribution, which is this. Right. Now I'm going to make a substitution. I'm going to set m equal to n minus 1, right? And then you can write the above as follows: a times the CF of x at V, sum from m equal to 0 to infinity of Alright, so this is the substitution I made, m equal to n minus 1. Right. Now once again, using the sum of a geometric series, which I mentioned in the previous slide. Okay. Using this result, you can simplify the sum. You can simplify the sum to the following: A right. All right, so this is the CDF of maximum portfolio loss, right, for the example 4, right. I just do one more example. This is example 5. Suppose suppose the losses are AID and the number of investments is a random variable with the following probability mass function. Okay, where n goes from 1, 2 to infinity. This one, if you don't remember, well, if you don't know, this one is known as the truncated. This one is known as the truncated Poisson distribution. Okay. So the question is once again the same: is to find the distributions of U and V. Okay, so let's start with U. The CDF of U is as follows: is using the formula I gave you a few slides ago. Okay. Now this you can rearrange as follows. Okay. Now in the next step, I'm going to use a result that you may or may not know this. If you have something like this, right, then it's equal to E of Z minus 1. So using this result, you can simplify the summation to the following. So this is, you can also simplify this to this, right? And So this is the Cdf of U for example 5. Now the next thing is to find the Cdf of V. So using the formula that I gave you, you can write this as the sum from 1 to infinity times the probability mass function, which is okay. This can be rewritten as follows. Okay. Right, now using the same result I mentioned in the previous slide, which is, let me write that again. So using this result one more time, we can simplify the above into the following. Right, so that completes example 5 and also completes case 2. In the next video I will talk about case 3.